machine with the nano features. So experimental setup, and we want to show you the experimental setup and also experimental results. And then we do the 3D FEM model and the validation of this FEM model. And then we talk about FEM numerical simulation results. And also, we have done something about molecular dynamics simulation. And I'm going to show you this MDS, the simulation MDS results also. So finally, I'm going to give you the conclusions. So here's the research motivation. So silicon. So this one is probably for the silicon. Silicon has been a very important material in industry for the applications in the micro and nano mechanical systems, MEMS and NEMS, and such as high performance sensors, semiconductor products, and others that are used in extreme environments. So this, some people call this age current age, we call this a silicon age, because the silicon is widely used in our daily life. So, however, the silicon has a poor machinability because of its high hardness and brittleness. So, in this research, a novel nano manufacturing process, which is termed vibration assisted, you can see that as the name suggests, a vibration assisted nano impact machining by loose abrasives. And the VANILA, this one is proposed. So this is the background when we propose this new nano machining method for silicon. So here, so it's existing, and some people use the other methods to nano machine the silicon and other materials, other brittle materials. So existing is a graphic and energy beam based nano machining. Often need the clear room environments and huge capital environments. So this is lithographic and energy beam and this based nano machining, and they are working very well, but they need the clear room environment and then the huge capital investment. So this is not widely available, widely not very good available option for nano machining. So their shortcomings include limited choice of work material and also chemical hazards associated with this graphical and energy beam associated based nano machining, and also thermal induced defects. So this is especially for the energy beam. So energy beam based nano machining. This is thermally induced defect on the machine surface. So this table gives us a comparison of this is the currently available nano machining methods and also the proposed methods. So look at here, we conducted a comparison in terms of the tool, machining force, thermal impact, the cost, and also these applicable materials. So this is for first method is nano indentation or the scratching. So this nano indentation. So the tool is used in this method is diamond tipped the probe. This machining force is high, okay? It's very high, and thermal impact low because there is no thermal, no heat is involved. And the cost is low. The applicable materials, this method can be used for materials such as metals and polymers. So this is for the first method. And second one is E energy. This E means energy beam method. So this electron, they use electron beam, right? Electron beam. Machining force is almost zero. They use the beam because electron beam. And the thermal impact is very high because this is electron, right? Electron. The cost is very high also. Materials, so this method can be applied for almost all materials. Another one is FIB. They use ion. They use ion beam, and this is machining force is no machining force because they use also ion beam. Thermal impact is high, okay, because they are using ions. The cost is very high, so this method is also be able to use for all the materials. So another one is laser. Laser is using laser beam. The Dr. Lei, as last time I introduced, Dr. Lei used the laser, 5-second laser, and to nano machine some very brittle materials. For example, silicon is one. So laser beam, they use laser beam. Machining force, no, because laser, right? The thermal high because the laser beam usually has very high energy, and the cost is very high. You need to build this energy laser system first. So all materials and almost this method can be used to nano machine all the materials we know currently we know. So another one is the photolithography method. So this is for MEMS. So the tool is used. The tool used in this method is ultraviolet light. It's ultraviolet light. Machining force is no because they are using light. And thermal impact is high also, and the cost is very high because you need to have this ultraviolet light system. So materials that this method can be used include these semiconductors and polymers. So this is the available nano machining. I will not say widely used, and I'll just say the 5 available nano machining methods. So this is the last column and lists the all this is these aspects regarding this purpose method. For purpose of the tool in this purpose method, we use loose abrasives. So machining force, we don't have machining force. The thermal impact is very low because we do not have this very high temperature. No heat is involved. The cost is low. The materials, and so this method can be used from all materials. Definitely, you need to change these abrasives. So here, so this is a schematic of VANILA nanomachining process. So here is an atomic force microscope. So AFM, tape. So this atomic force is used as a platform, and nanoabrasives is nanoabrasives inside. Okay, this is the slurry. This is the slurry. Injected in the slurry between the workpiece, this workpiece, and this is the tool. The vibrating AFM probe is vibrating. So this is AFM probe. This guy is vibrating and impact the workpiece and result in nanoscale material removal. So when this guy is vibrating, so this abrasives, and we call abrasive grains or abrasive, and these abrasives will be vibrating in the slurry also, right? So in this, you going up and down, and so they can just remove this area, this material. So here we will have a cavity, so we can just remove the material. So here, the impact velocity of the nanoparticles is about 100 to 200 meters per second. So here is the workpiece. So this is thermal zone, and so here is the elastic zone. So this is, we just use a single abrasive grain to illustrate how this method works. So this guy is vertically impact on this workpiece. So here we use this is a schematic representation of VANILA process. And here is the silicon. So we use this is the green, light green, and to mimic this represent this is a slurry, and these are dark circles, and they are this is the diamond particles. The abrasives here used and are these diamond particles. So here is active particle. Why we call this active particle? Because AFM2 tape and heat this guy, and so this guy, when this AFM2 tape vibrates, so this guy will be vibrating also in the slurry. So as a result, here you can see when it goes down this way, so this active particle will come here, right? And then because the impact, and we can have this is a tiny circle, tiny this cavity here. So this is this picture and shows how this is a vanilla method works. So this new method can improve the nano machinability of a wide variety of both conductive and non-conductive materials. So this method may have applications in biomedical, electronic, automotive, energy, and metalworking industries. The potential applications include this is a nanostructured scaffolds in this biomedical application, and for artificial tissue engineering, nanostructured switches and wireless transmitters, and ultra-low diffraction layers, and for thermal barriers coating or coating material, and nanostructured proton the exchange membranes and for fuel cells. So this is the potential applications of this is a vanilla nanomachining method. So here the experimental setup of the vanilla. Also, so we have this piezo control tool head we have here. So we have a tungsten tool. This is a tungsten tool here. And we have a machine cell. So this is zoom in, okay? So this is a machine cell. And so this is vibrating piezo stage here. So this is a manual course approach. And so this is Arduino, this is a feedback, this is control. So this is the setup of this system. So aluminum, so in this setup, experimental setup, aluminum coated silicon is a silicon wafer of rectangular shape are chosen as a workpiece. And the workpiece is placed in a machining cell and introduced between the tungsten tool, the tool tape, radius of 147 micrometer, and a sample plate. The substrate, the substrate is vibrated as just below its resonant frequency and in this range, 60 to 12 kilohertz. You can see that this kind of different from what I show you at the very beginning. So experimental, and as long as you can accomplish the relative motion between the tool and workpiece, that will be okay, right? So previously I said the AFM, the head is moving, but not this time. And in the experiments, so this is a stage, workpiece stage is vibrating. The same thing. Nano diamond grains of 10 nanometer size are used as an abrasive material, which is mixed with deionized water to form slurry. So this is a slurry contains the deionized water, and this is abrasive. This abrasive, diamond abrasives. The abrasive slurry is introduced on workpiece surface using a syringe before the machining process. So here is the experimental results. The experimental conditions are given here also. The machining height means that the distance between the workpiece surface and the tool head, the tool tape. Vibration frequency. So how frequent the frequency the stage is vibrating, and the time of machining. So how long it takes to machine this. So that definitely as the size of this hole and also the depth are dependent upon the time of machining. So here this is the in this direction 1.64 micrometer, and in this direction is 1.06 micrometer. So this is not a very the perfect circle. Here, this one, this one is more circular. So experimental conditions are given here also. Machining height and 0.3 nanometer. Vibration frequency, this time we use 9 kilohertz. Time of machining, we use 30 seconds. So this is very, very circular. So here is 746, and this is 764, this is 760. It's in two orthogonal directions, and the dimensions are very, very close. So here is another one. Machining height 0.1 nanometer, vibration frequency 9 kilohertz, time of machining on 15 seconds. So here is for this time it is not very, very circular. We can see this dimension and this dimension, and they are not very, very close. So then this up to now we talk about experimental setup and experimental results, and then we talk about the numerical modeling of this VANILA. Okay, so numerical modeling, and we use the finite element method to model this is a nanomachining process, and we also use Abacus. And Abacus is our old friend, and we have used them a lot. Okay, for me, I use Abacus almost every day. So Abacus is employed to model and investigate the phase transformation and the crack propagation of this is nanomachining. So Abacus explicit, and we know that we have Abacus. This is a standard. Now this is Abacus explicit. Has been run on clusters at the St. Louis University, and we have a very, very good cluster. It takes very, very long time. That is reason, and we cannot use our the computers in our office. We need to use a cluster. Okay, cluster we have more computational resources. For example, very, very big the memory, and very, very fast. This is the CPU. Many CPUs. And this is cluster is a very, very good tool that we can use. So this provides insightful guidance to improve the capability and performance of VANILA machining method. So you can see the research includes the experimental and FEM and also numerical. So currently, the funding agencies, the federal funding agencies, and they want to fund the proposals that combine both experimental and this is numerical. And why numerical modeling is important? Because I look at some experimental results, and for some experiments, and they are very, very difficult to conduct. It's almost impossible. Under this condition, we can do some modeling. Okay, modeling, we can reveal more science and inside this is any kind of physical processes. So that's the reason currently federal agencies, for example, this NSF, National Science Foundation, the NASA, Department of Defense, Department of Education, and also Energy, Department of Energy, and they emphasize that they want to see the proposals that combine both experimental and numerical results. So here is this numerical modeling. So we have this workpiece because of the nature of this nanomachining, we can know that. So here is we just assume this one is a circle, is a sphere. The size of the workpiece, we have this 40 by 20 by 10, and this is a nanometer. And so we use, as you can see, 3.5 million. This is elements are used. And particle diameter, we use 10 nanometer. The particle is treated as a rigid body. Okay, because when we compare the hardness of the diamond and the hardness of silicon, we can see this particle or diamond can be treated as rigid body. Because the brittle material, we use the drug-Prager, the constitutive model, to describe material behavior of the workpiece. So the drug-Prager, maybe you are not very, very familiar with this one, or you have never heard of, this is a constitutive model. But I want to show you guys, plug plugger is suitable for modeling these brittle materials. You can see we can only use this half of this workpiece and half of this tool. We call it tool also. Half of this is diamond abrasive. Why we can use half? Because the symmetry, right? Because the symmetry nature of this nanomachining. So here is a workpiece. So here in this area, we want to use this is a very fine mesh in order to capture the stress gradient and also strain gradient. So that's the reason here in this contact area between the nanoparticles and workpiece, and we use very fine mesh. So here is the silicon, and we give the silicon, so mechanical properties for silicon. This includes elastic modulus, hardness, Young's modulus, and Poisson ratio density along with the fracture energy. Fracture energy means that how much energy you need to apply before this is the material fractures. So the silicon, this is the traditional units. Okay, this is SI units, traditional units. Because we are handling this nanomachining, this nanoscale, and we need to calculate these nanoscale units that these are from these. But pay attention to the units, because in abacus abacus does not have its own units. It is totally the researcher's responsibility to handle these units consistently and correctly. So this is the basic dimensions. Length in nano diameter, and force we use nano newtons, and time we use time. Time use second. Time does not matter. Either in the SI unit or English unit, we use the same time, the standard time. Standard unit for time is second. And for this nano, the scale also, we use the second as a standard unit. So also, for nanoparticle, for the tool, we call the tool. For the diamond, we have the size. Size is given. This is 10 minus E meter, right? The meter, because the meter is a standard unit. The density also is given here. Is from the reference number 1, 3,500 kilograms per cubic meters. So these are traditional units. We also, because the diamond is also used in this nanomachining context. As a result, we need to scale these units down, nanoscale units. We have 10 SM and also this number. You can see this only taking care of the factor, 10 power something, 10 power some number. So this is table 3. Table 4, the drug program model parameters for silicon. I told you a drug program model is used for describing the behavior of brittle materials. So for drug program model, we have friction angle beta, and deletion angle is 5, and flow stress ratio, and it's the lowercase k. So these 3 parameters need to be selected in order to use the drug program model. So here are the basic dimensions, the same thing. Nanometer, nanonewtons, along with this second. So here is a phase transformation flow chart of silicon. So, and the silicon is a very important material, and different pressure, and you will have different is a phase. I told you guys how do we define a phase? How do we define there are multiple phase, or this is there are different phases, or they are the same phase? So the phase means that for the same material, okay, same material, as long as there is one different physical property or one different chemical property among them, and that means they are different phases. You have sense? As long as one single either physical properties or one single chemical properties, if they are different, one of them is different, and these two guys are even the same material are different different physics. So you can see for different pressures, they will have different physics. You can a lot of physics for silicon. Diameter cubic physics is original one for the workpiece, and polycentered tetragonal, and this condition, okay, 11, if this is 11 gigapascal and this pressure is also cubic, is at the 13 gigapascal pressure, a simple hexagonal, and then 15 gigapascal, we have silicon, silicon 4, silicon 3, silicon 2, the original one, we denote this guy as a silicon 1. So this is also cubic. This is a silicon 4, a silicon 5. It's from 15 to 38 gigapascal, and the silicon will have this material. That this kind of crystalline is the structure. So silicon 6 is from 38 to 42. So we have this is sometimes we have this arrow going down. Arrow going down means the transformation direction. This going up means that for this one, silicon 6, if you reduce the pressure, and you can come by, you can just get this silicon 4, silicon 5. The same thing here. If you reduce the pressure, you can get this silicon 4 here, right? And for this one is silicon 2. If the 10 gigapascal, you will have get this silicon 9, we call silicon 9, and this is go down further to 3 gigapascal, and you have silicon 6, silicon 10, I'm sorry. So here is the silicon 8, so here is silicon 7. 7, 8, 9, 10. You can see there are a lot of physics for silicon and different contact pressure. This is solid arrows stand for loading. These dotted arrows stand for unloading. So here is a flow chart, and for this is implement. This is here numerical modeling flow chart. These are silicon stars, material parameters initialized. Look at here. Okay, so here as for the phase transformation, and so this is we use S field for phase transformation output. So this one is a subroutine. Abacus does not provide this one, and you need to use this is the Fortran. You use the Fortran language to write your own subroutine, and then you link your subroutine and to Abacus, so the Abacus can do the analysis for you. And the next step requires the stress tensor for calculation of hydrostatic pressure. Okay, so here all this is physics. They are dependent upon hydrostatic pressure. So evaluate the value of hydrostatic pressure for each phase for loading and unloading, and then updated silicon physics based on the current hydrostatic pressure value. If the simulation is completed, we stop. Otherwise, move back and go to the next time step. So this is the flow chart and to implement the phase transformation analysis for Abacus. And during this is a VANILA nanomachining. So here is a variation of elastic modulus. So because the silicon's elastic modulus, or we call Young's modulus, and also hardness, and they are temperature dependent. And we get this curve, and we have these for 3 points, and then we use this linear, the straight line, to interpret. So this is values for these temperatures in between. So here is a numerical modeling of VANILA. These experimental pictures and show no cracks. You can see these experimental pictures and show no cracks on the top surface of the workpiece of the machining. That means that total damage model has been used for numerical simulation because we cannot have any cracks here. So here's a nano cavity on top surface on workpiece of the machining. So this is a cavity. The cavity. This is diameter, and so here is the diameter, and this one is the depth. So down-to damage model has been used for numerical simulation. In Abacus, the damage variable we use the D, the dark CRT, the critical. CRT means critical. In Abacus represents how much damage of the element suffers. So this is D. Okay, so this is D. Look at here. So we are familiar with this curve, right? So this curve is much smaller than the speed hardening. And here, and here, right? So this is yield stress. This yield stress here is used. So this is Y0 here. And from here, if you just take away your load, and so this is the material is going to behave this way. So this line is parallel to this line. That's the reason the slope we use Young's modulus. However, if you go further, right? Go further, this is D at the very beginning, this is D0. D0 means that no damage. No damage. However, as this is a plastic strain increases from here, this damage value goes this way, this way, this way, this way. And you can see the slope of the curve also decreasing. 1 minus dE. When D equals E, that means the slope equals 0. Okay? The slope equals 0 means that this structure is totally cannot carry any load. When D equals 0 means no damage. When D equals 1 is fully damaged. So here, the reaction force, and I told you many times, whenever we do some experiment, numerical simulation, and we must validate our numerical results, right? So in our research, we use the reaction force is used to validate our simulation. So this is the reaction force, analytical reaction force. This is the P, is the pressure, the force. Force. So this N is here, okay? N is depends on these two guys. You have Young's modulus here, E2, R1. So you can see nu is the velocity. V is the velocity of the impact particle. R1 is the radius of the impact particle. M is the mass of the impact particle. And E2 and V2 are the Young's modulus and Poisson ratio of the workpiece. For our case, the silicon. So in order to capture the reaction force, the impact reaction force, and we attach, my student built a rigid plate and attach this rigid plate on the bottom of this workpiece. The rigid plate, and for the rigid plate, we can capture the history of the reaction force, as we did in our this metal forming Abacus assignment, homework assignment. You can see this is numerical modeling. So here is the validation. We compare the simulation results with the analytical results, and they are for two different impact speeds, and they are very, very close. So you can see here is an animation of vanilla machining process. So this is done by my student Nick Dong. Then there's operating parameters used in phase transformation investigation. Impact speed, right? This impact speed. Also friction coefficient between nano-abrasive and workpiece. Whenever we have impact, so we need to take care of the frictional coefficient between these two objects, two atoms. So we use different materials. And it depends on the condition that you use. And you might have this number for the frictional coefficient, or you might have these other two numbers for the frictional coefficient. And also the impact angle. This is impact angle. This is 20 degrees. Impact angle is angle formed by the vertical line and this and here this is direction, right? So this is the impact angle. So we try 20, 40, 70, and 90. 90 means that it is a vertical impact. Here see, this is the phase transformation. The pressure distribution on the silicon workpiece for this machining condition. You can see the volume also. So this is the pressure. So this is the green one, the red one, this color, and also the light green and the green. So here is the FV1 is the visual field. We have with this domain. And so we have this is silicon 7, and so this color is the silicon 8, and so this is silicon 10. And so this is 3 different phases. And so then we can, based on this cutting conditions, we can use this multiple linear regression and to predict at any combination of this cutting speed, impact angle, and frictional coefficient, we can get the silicon volume for the silicon 7, volume for silicon 8, and volume for silicon X. This X means 10. Okay. So that damage evolution investigation. We just talk about the phase transformation, and we talk about damage evolution investigation. So here are the impact angles 20, 90, and 90, and the coefficients. We have this one, this temperature for different temperature. For this impact angle, we have 6 temperatures. But for this one, we have 1 temperature. Impact speed 20, 200, 200. For this case, we have 5 different impact speeds. So here, excuse me, the damage evolution of silicon of the feed. Okay, we force out one single abrasive feed number. How many times you want to feed? A is 0 is the very beginning. B is 5 feeds. C is 10, and D is 15, and E is 20, and the last one is 25. So this is for impact velocity. You can see it is increasing. Right? This is the damage. So this color means the damage removed, material removed. So here's a comparison of damage volume in workpiece at different frictional coefficient and the different frictional coefficient. It's 1 and 2 and 3. So this one is very, very light, but it's very difficult to see. But it is 0. This is number of pieces. Right? Definitely, this volume, damage volume increases as the number of pieces increases. So this is the comparison of damage volume in workpiece at different temperature. 200, 400, and 600. This is 200, 400, and 600. 200 means from here to here, and below 15 or 17 Ps, and don't have any damage. And for this 200 temperature. But for this one, at the very beginning, we will have some Ps, and we will have damage volume. Also here, as the temperature goes, temperature is higher, and it is much easier to get damage. Material removal, I'm talking about material. Damage means the material removal. At different impact velocity, 175, 200, for different velocity, and also number of Ps. So this is the damage volume. And temperature, we fix for both of these two cases, we are using 400 degrees C. And this is the IBM model. And then we talk about MDS modeling. Have you guys ever heard of this MDS simulation? No. The molecular dynamics. So this is IBM is different from this MDS. MDS is molecular level or atom level. Okay? And so this is that's the reason the MDS can model the chemical reactions. So that's the reason the chemistry department and physics department, they use this, not just our engineering department. So here you can see that this is atomic level. So this is also this is abrasive, a lot of abrasive there. Here is a silicon substrate, and this one is thermostat layer items. So this nanoparticle is impact angle. So this is theta, impact angle theta. You can see, when you heat it, and you will get this cavity. So where this cavity, okay? So this cavity, because originally you have atoms in this space, but after you heat it, so this for some reason the break, because the heat force exceeds the bond between the atoms, and then the atoms they are removed. So here are the different. This is 40 degree, and this is 80 degree. The time is 1 picosecond. And picosecond means that 10 power negative 12, right? So picosecond. So the energy is 500 electron volts. Electron volts is very, very small, because the nanoparticle, right? Nanoparticle is very, very small energy. And here are the conclusions. So a novel nanomachining process, VANILA, is proposed to nanomachine the brittle materials, for example, silicon, graphene, glass, etc. Experimental results show the feasibility of these nanomachining processes. FEM and molecular dynamics, what we call MDS, are used to model this nanomachining process to investigate the impact of machining parameters on performance of nanomachining. So simulation results can provide insightful guidance to improve the controllability and performance of the VANILA machining method. So these are references. So this is acknowledgements, and the thanks go to the